In class this week, we talked a lot about sampling distributions and how the greater the sample size, the better of an estimator it is for the actual mean of the original data. Looking at examples such as rolling dice many times in many quantities, or taking random people from a population to see what their height is. And the central limit theorem is the thing we finished up with, and I just wanted to reiterate, the idea is that if we take a large enough sample size, that sampling distribution will be normally distributed because it is more likely for you to obtain a sample which mean is the same or close to the actual mean of the population. More likely for that to happen than to get an absurd, like a mean that is much lower. Like in the case of rolling groups of 5 dice over and over again and determining the means of those groups of 5, we had way more results that were 3.5, 3.6 that were around the mean and value around the actual mean of rolling dice, and when many fewer results when it was smaller. Like we only had a couple results where the mean came out higher than 5 as well. But basically and we're going to use this idea to calculate and to use the normal distribution to figure out how close a randomized mean is from the value. And the biggest thing to remember is that whatever our population distribution may be, regardless of whether it's normal or not, the sampling distribution will be normally distributed with a standard deviation that depends on the sample size. So like in this case, when we were rolling 5 dice, we say n is equal to 5, and that is the formula for n, which affects the standard deviation of the normal distribution, which is of the sampling distribution. And we looked at a couple examples of why that was. Basically, when you're taking more and more data points, it is way less likely to get an outlier for your mean. Like rolling 5 dice 400 times had a much larger standard deviation. We had some instances where the mean was quite as significantly higher than the expected mean of 3.5. But when we rolled 10 dice, way less frequent to get absurd values. And if you roll 100 dice, you'd expect it to be even more normally distributed and getting closer and closer to the mean, as is the nature of the law of large numbers. But what I wanted to do in this video is talk about actually using that, and let's apply it to a particular example. Let's go ahead and work on the next example from the packet. And the question says, consider rolling a 6-sided die. A die roll is an equal probability event and most definitely not normal. As we said, every outcome on a die we're assuming is a 1/6 chance to roll a 1, 1/6 chance to roll a 2. And in practice, if you roll a dice 100 or 400 or 1,000 times, you're going to get a fairly even amount of values of each roll. But regardless of whether the event is normally distributed or not, which it isn't, we can still use the central limit theorem to solve a question like the next one. Is what is the probability that in 10 rolls the mean x bar is greater than or equal to 4? And one other thing to point about at the central limit theorem is it says that when n is large, that's not exactly very, what does that mean? How do we know what n qualifies as large? But usually probably 10 is not necessarily a large sample, but it's relative to the original population size. You might say 0.1% or 1% or whatever, depends on the size of the population. When it comes to a roll of a die, it doesn't really make sense because every outcome is random. But anyways, let's go ahead and practice applying the central limit theorem to try and figure such a question out. So let me move down to the lecture notes, which is down here, and the question is below. And if you're filling in the blanks, the central limit theorem is the answer to this blank, which we can fill in. Okay. But let's look at question number 5. It says, use the central limit theorem to approximate the probability that in 10 6-sided dice rolls, the mean roll x bar will be at least 4. Or, we could write this as, x bar, which is the mean value of those 10 rolls, should be exceeding 4. And probability notation is something that we used a little bit with z-scores in the cumulative distribution, but what we kind of what we want to know is what's the probability of that occurring. But basically, the rule of thumb, going back to the slides, didn't really think this organization of my handouts very well, is step one is we want to adjust the standard deviation. Figure out, well, okay, I have my original standard deviation of the population. Again, in reality, finding the standard deviation of an entire population, we might not necessarily know what this will be. But, you know, we have to know this in order to solve things involving probability sampling distributions, I mean. But basically, we would want to take the original standard deviation and divide by the square root of n. So looking down here, the new standard deviation for the sampling distribution always can be given by this formula, which would be equal to 1.87 divided by the square root of 10, which is always how many people are you taking from your population, or how many, you know, events do you, in this case, 10 rolls of the die. So let's go ahead and calculate what that will be. 1.87 divided by the square root of 10, which comes out to be approximately 0.59. And we looked at some sampling distributions with 10 dice rolls, and we let's see where it was. Sorry, again, I should have done this a little bit better. Up here, we looked at an example where we looked at a sampling distribution where I rolled 10 dice 200 times and displayed the result. So this would be the sampling distribution we're talking about. And again, this would be the standard deviation approximately of this. And notice that, again, when you have a higher n, you have a more tight set of data, smaller standard deviation, less variation than when you roll less. There's a lot more variation with smaller sample sizes based on that idea. But what we could do next is we could actually use this. So again, applying the central limit theorem means that our sampling distribution has this standard deviation, and its mean is equal to the mean of the original population. And so if we wanted to know, well, what is this? What is our z-score value here? We could actually convert our desired probability. So we want to know the probability that x bar is greater than or equal to 4, and we can convert that score to a z-score. So that would be equivalent to, well, what's the probability that the equivalent z-score is greater than what? But, you know, the question is, what is that z-score that corresponds to x bar being 4? And so basically, you know, we could just use our z-score formula. Z is equal to x minus mu divided by sigma. And notice here we want to use our new standard deviation because, remember, for a normal distribution, this refers to the standard deviation of the normal distribution, which changes because in a sampling distribution, it's smaller than the original. And that's a really easy thing to forget to do if you're not careful. So our score is 4, our mean is 3.5, because remember, the mean of a sampling distribution is the same as the mean of the original. And then we're going to divide this by 0.59. So this will give us our approximated z-score, 4 minus 3.5, divided by 0.59. And this would give us approximately 0.85 as our z-score. And so that's exactly what we wanted to know, is what's the probability that our mean will be greater than 4? Well, that will correspond to having the probability of the z-score being greater than 0.85. And then we could figure out what this probability is. Again, if we think about what a z-score means, it has to do with a normally distributed curve, which is exactly what we're looking at with any sampling distribution, the whole point of the central limit theorem. But basically, the mean here is going to be 3.5, and we want to know, well, where, you know, remember, if we're graphing z-scores, the center is always 0, but basically we want to know what's the probability that we're going to be greater than 0.85, which would be a little less than 1 standard deviation to the right of the curve. Again, don't have to be exactly perfect with my graph, but this is what I'm looking for. And so I want to go to the z-table and look up what's the cumulative probability of 0.85 and subtract it from 1, because remember, that table always gives us the left-hand side of the z-score. So I believe I have that z-table in the slides here, wherever it is. Again, I should have thought through this layout a little bit better. Actually, it looks like I have it here somewhere. So if we want to know, well, where is Z 0.85, right? 1, 2, 3, 4, 5 right there, about 80%. So 0.8023. Let me go back to my handout. So this would be 0.8023. And so of course our probability would be that we're looking for is going to be 1 minus 0.8023, which would leave me with approximately 19.77%. And that would be the probability that our mean would be greater than or equal to 4. And so again, kind of summarizing this idea is that, you know, when we're going to roll 10 six-sided dice, the mean we don't know what it's going to be, but since we know the distribution will be normal, we know a percentage which is associated to a more extreme outlier. And I would say having a roll greater than 4, that's not super extreme, but notice all of these calculations are based on the standard deviation. The larger the sample size, the smaller the standard deviation, and the smaller of a chance we're going to have, because the standard deviation is taken into account right here when we're calculating our z-score. And if we only took one sample, it would be basically you'd have the original standard deviation, which would be much less likely to get a particular outcome that we're looking for. And I wanted to go back to the slides because it had this graphed over here. But again, all this math is laid out in the slides. But notice that actually we already did this. One of the examples I talked about in class is, say we rolled 10 dice 200 times, and I graphed out the display of the sampling distribution for this case. But notice if you actually count up the number of times that I got a mean greater than or equal to 4, well, I didn't do a great job of showing it in that, but we had roughly 17 or 18 counts where the mean was higher than 4.2, and then we had roughly 35 counts where the mean was higher than 3.8. So if you say this is probably going to be 20 to 30 values which are higher than 4, and this one would be about 17, but basically, you know, roughly it's going to be 30 to 45 values which were, and I could go back to the data and actually count it out, but I didn't do that. So, well, we can just kind of catch the idea here, but roughly about 19% of those scores are higher than 4. If I would have done a better job with the histogram, I could have shown exactly how many we got, but notice the probability is in line with that which we got. And so, sort of just to summarize once again, if you want to use the central limit theorem to determine the probability that your mean will exceed or be lower than a particular value, you just want to figure out, well, okay, what's the standard deviation of the sampling distribution? We know it's going to be normal, so therefore we can find the z-score for our score using the new standard deviation and figure out the probability of that happening by using the z-table as we did back in chapter 3.